So now our last speaker is Naomi Vaughan, talking about how to get to net zero. It's a very appropriate follow-on there. Nem's an associate professor in climate change at the Tyndall Centre, and she has done a lot of different things, but mitigation and actually taking greenhouse gases out of the atmosphere, negative emissions, has been one thing that she's focused on. Nem.
The other slides, I'm looking at
the end of this, so keep going through them.
Sorry.
Should have done that. That's okay. Hey, thank you very much. First of all, thank you very much for the introduction. I feel quite a small fry after the previous two speakers. So what I wanted to talk to you today, actually, Malta kind of, I'd seen his slide deck, but he did skip over some of the slides. So I want to talk to you about the role of carbon dioxide methods in how we get to net zero. So all the stuff we need to do about decarbonisation is a given, but I want to talk about that. What I want to cover, I want 3 points. I've got 12 minutes, 3 points. You'll note me talking faster, as is my habit. I apologise. And the 3 things I want to cover is the functional role that carbon dioxide removal plays in getting to net zero greenhouse gas emissions. I want to cover very briefly, I do most of a master's module on this, but the different methods of carbon dioxide removal that are in some of those future emission scenarios that have been referenced today throughout the talks, what's in and what's not in. And then I want to the focus of my research has been points 2 and 3 a lot in the last kind of 5 to 6 years, is about the feasibility of some of those methods. I fear I will not do as well as our PhD students on keeping to time. I apologise in advance. So very briefly then, we've seen figures like this. This is from, again, Working Group 3, Summary for Policymakers. On the left, all greenhouse gases. On the right, CO2 emissions. The kind of orange wedge has been referred to in previous talks, the kind of current policies trajectory or the moderate action scenario. And what we're thinking about is the ones that get us in this 1.5 and 2, the purple and the blue space. So one is gigaton CO2 equivalent, the y-axis, the other is just CO2. But you can see they're on the same y-axis scale. So you can see that greenhouse gas emissions get to 0 by the end of the century. In some of those 1.5 scenarios, that's happening more like 2050, 2060. Others, it's a bit later. But you can see the main take-home message is that CO2 is getting to 0 sooner, and it is being more negative, okay? And so this kind of, what's to get the carbon dioxide removal method, sometimes called greenhouse gas removal or negative emissions, is the stuff that's going to get you below that 0 line. And it plays 2 roles, actually. And again, this is, Malta was mentioning it in relation to Miles Allen's phrase of durable net zero. But it is about, the first role is residual emissions. So those scenarios you're looking at there on the previous slide, here, this is a stylised pathway, another summary for policymakers, or it's a cross-chapter box, actually, figure. The solid black line, then, relates to the left-hand panel on the previous slide. That is net greenhouse gas emissions, and the dashed line is net CO2 emissions. So again, those patterns we saw on the previous slide are reiterated. You're getting to net zero CO2 before you get to net zero greenhouse gases, all greenhouse gases, and your net zero CO2 is going lower. The point, if we just look at our positive values, we have emissions mostly from managed land. Most of this emissions in brown will be deforestation. You can see our fossil fuel use. The way we mostly get to net zero is stop burning the fossil fuels. We get down to a very small amount at the end of the century. But you can see that the non-CO2 emissions, non-CO2 greenhouse gas emissions, mostly methane and nitrous oxide, mostly coming from agriculture, from fertilizer use, and from livestock and ruminants. It gets smaller, but it ends up being quite a significant fraction at the end of the century. On the bottom, you see we do have some removals, some carbon dioxide removal takes place today based on how we cultivate our land and our agricultural practices, but also based on afforestation schemes, natural regeneration, and the management of forests and agriculture to give us the darker green colour. But the thing that's quite meaningful, and again pointing towards this durable net zero that was being mentioned, is this thin lime green wedge of other removals, most of which in the models are either BECCS, biomass energy with carbon capture and storage, or direct air capture and storage, DACS, BECCS and DACS. And what they are essentially doing is creating a new carbon sink. You're taking CO2 out of the atmosphere and you're storing it in certain geological formations, either old oil or gas wells or saline aquifers, or in some niche cases, putting it into basalt so it directly carbonates into mineral. So what the CDR role is playing is it's doing two things. It's offsetting. At the end of the century, we've still got, even though the black solid line is below zero, we've still got positive emissions. These residual emissions are likely to come from agriculture, as we've just talked, in the orange colour, but also things like aviation are difficult to decarbonise, not impossible, but very difficult, and certain forms of heavy industry are quite tricky to decarbonise. And so you need some of the carbon dioxide removal to counterbalance those residual emissions at the end of the century. But then you see that our green down arrow is much larger than our brown up arrow. And to get those net negative emissions, to get all greenhouse gas emissions below zero, that's why you need even more. And that's the second role that carbon dioxide removal plays, is to give us that ability to go below zero. So the residual emissions allows us to get to zero, counterbalancing residual emissions. The CDR then allows you to go beyond that for net negative emissions. Basically, all of this is trying to scrabble back from that overspent carbon budget in Malta's pie charts. So what methods do we have then? This is another summary diagram. It's actually based on Jan Minx's paper in 2018. It's trying to cover a lot of stuff. So I'm just going to walk you through it in kind of big chunks. I'm not going to describe everything in detail. Just to say, on your far right, the ocean alkalinity enhancement and ocean fertilisation are mostly the stuff of scientific research and some controlled small field trials at the moment. Enhanced weathering, actually, is in the dashed red box, is similarly in that position, something that is being most of it. So these are things that are at a much earlier stage of research and development. Blue carbon, as it's termed, is things like planting mangroves in tropical regions, planting seagrass meadows, so that's on shallow sedimentary coastal areas, and salt marshes, something we do a bit of in East Anglia. Then we have other methods of basically managing or trying to enhance the carbon sink on land. So things that are changing agricultural practices over here to do with soil carbon sequestration, getting more carbon into our soils. Biochar is one particular way you might do that. There's lots of different things to do with planting and using trees on this left-hand column that we can do. And then we have our two that I mentioned earlier, the BECCS and the DACS in the middle. Now I've highlighted in red the ones that are in the future scenarios. The dashed line around enhanced weathering is because it's in there, but only in a tiny amount in some scenarios, which I'll show you in a second. So the point is there are lots of carbon dioxide removal methods. Most of them, apart from those open ocean ones, are things most of the ones that are not surrounded in red, in fact, are things we do today. So they're things that we do today, and they're things we do for other reasons. They have other co-benefits. We've got peatland, sorry, I didn't mention peatland restoration as well in there. The biomass energy and the direct air capture, though, they have this link to this durable net zero in that when you take the carbon out of the atmosphere, either by using nicking on the back of the work of photosynthesis with the biomass has taken the CO2 out for you, you then take that biomass and you use it in some energy conversion process to get something useful out of it, then you capture the CO2, transport it and store it deep underground. The back part of that process, the transport and storage, is the same for direct air capture. It just captures the CO2 rather than piggybacking off of photosynthesis that's happening. It just uses chemical engineering methods to scrub the ambient air. So for those of you with any chemistry background and those of you who pay attention to the fact we measure CO2 in parts per million will spot that that's quite tricky and has quite an energy demand to pick something up that's measured in parts per million. So there are lots of different methods, they have lots of different benefits and side effect, challenges and issues, each of them, but just to note, the ones that are included in the model are in red, and to pack that up, this is a nice screen figure from Glenn Peters. He likes churning out lots of plots on Twitter. This is just the 1.5 degrees C scenarios in the AR6 database, and you've got top left BECCS, top right DACS, so the two that are doing the same capture and storage part, but catching the CO2 out of the atmosphere in different methods. Afforestation, bottom left, and you can see why I only put a dashed line around enhanced weathering. There's barely two scenarios in this one. So integrated assessment models that are used, the IAMs that are used to generate our future emission scenarios include CDR methods that are easy to include in their model. These are models of the global energy system, and they're models of the global energy system with a representation of the emissions. Some of them have a land use kind of figured out spatially, others just assume a certain amount of biomass resources available. So the reason that there is, you can see easily from this pattern that BECCS is dominating. Secondary is afforestation, but you see DACS takes over at the back of the century for that. The reason that BECCS is chosen over DACS for a cost-optimized pathway is that BECCS is giving you something useful. It is contributing to the energy system. It might be contributing electricity, electricity and heat, a liquid transport fuel, or some hydrogen potentially. DAX just costs you money to do. Big arguments in the kind of innovation space around DAX. Everybody who's innovating it thinks they've got a special method that means they'll get their costs super low. Then you start to poke around what they mean by their costs. But in this kind of framing, the DAX it doesn't provide anything positive other than just taking carbon dioxide out of the atmosphere for you. The afforestation is not all forms of tree planting. It is just a kind of expansion of new land area into forest, and it often is tied to a timber kind of fraction. So all of those from the previous slide, sometimes called nature-based kind of methods, are not in these models, because but those methods are predominantly ones that take place today and have other co-benefits, which just leads me in then to my point about feasibility. I'm going to make 2 points on each slide. The first one is the big conversation and discussion about sustainable biomass and land availability. Right? It's a kind of ongoing challenge here. And just to say, even if there was no BECCS in any of these integrated assessment models providing some carbon dioxide removal, you still see a massive increase in bioenergy use over time in these future scenarios, because the bioenergy has this role in decarbonising energy supply. So all the issues with sustainable biomass and land availability hold. For BECCS and for getting carbon dioxide removal, it really, really matters that the biomass is done sustainably. And by this I mean, don't chop down tropical rainforest to grow a dedicated energy crop, because you will have released so much carbon in that land conversion step. It doesn't matter that you're pumping CO2 down into an old oil and gas well at the end of it. You're still, as the climate system considers, you're still a net release of CO2. Okay, so you can do BECCS so badly it doesn't do carbon dioxide removal if you do your biomass unsustainably. Something that a lot of those AR6 scenarios use, for the ones who report their split, which is about half the scenarios, 40% you assume residues. So the advantage of residues, whether it's forestry, agricultural, industrial, or municipal waste, range of different sources you can get these residues or waste from, is that they have no additional land area, so that's a win. However, they do have some current uses in different places, and so they might not be completely without challenges. When it comes to this question, I'm continuously asked for a number about the amount of available land, and it is an impossible number to give, partly because of all the mess of trying to define marginal or degraded land to start with, but also because it's so codependent on our food production system assumptions out to the end of the century. How many people, what they're eating, and what crop yields we're getting, and how those crop yields respond to the impacts of climate change. So the carbon capture and storage use is the similar bit between the BECCS and the DAX, this durable net zero that Miles Allen likes, for example. It's a good take-home thing to always remember when you see CCS. CCS, the carbon capture and storage, if we bolt it onto power generation, makes power generation less efficient and more expensive. On current post-combustion systems, you're using about a third of the power to just power the CCS bit, right? That's why we don't do it today, okay? It's pricey and difficult. The storage capacity is sometimes glibly thought of as that there's tons, it's fine. But if we're going to continue doing this beyond the end of our graphs at 2100, if you actually poke around at the quality of the regional assessments of storage, if you actually think about what's most accessible and cheapest to get to, it does become a concern. And also that even if we had no BECCS or no DAX, CCS is still needed to decarbonise other sectors of the economy, specifically industry, things like steel, cement and chemicals. They have very few other options to decarbonise. So the CCS is in competition not just to do carbon dioxide removal, but also to decarbonise industry. And again, beyond 2100, if you still want to be able to make steel and cement and certain chemical processing, then you need some of that storage capacity available to decarbonise industry. So my final 2 points are around thinking beyond cost and carbon. Well, if we think more broadly, there are many more broader societal objectives, and this is hinted at in some of the earlier talks today, that need to be met by these decisions. So about carbon dioxide removal, it's not always just the best one that's cheapest and gets you the most carbon. You have to think about the impact on biodiversity, human health, well-being, livelihoods and communities. So you might have a different mix of positives and negatives there, and that might mean very specific trade-offs between carbon removal and meeting broader societal objectives. And it was actually on one of Malta's slides about tree planting is always good unless maybe monoculture spruce. Right, so this monoculture issue becomes a problem, for example. So there is, even in tree planting, it's not all unproblematic. And so in some cases, the carbon removal might just be considered the co-benefit, not the main driver. The positive in all these is there might be other reasons to get them done. When it comes to social feasibility, there's issues around governance and institutions. So in the modelled world, it's very easy to say we're going to protect food, we're going to protect forest areas, and then we're going to grow some bioenergy crops. Look, it all works out and everything's fine. In the real world, in practice, It is environmental governance and the quality of that environmental governance and regulation that makes sure you don't end up with bioenergy crops causing problems with food production. And so it's the governance that will determine the sustainability of the biomass. One final points then is around actors and institutions. If you want to get some of these more like farmer-based solutions done, they have lots of these co-benefits. There's lots of good reasons to do them. They meet broader societal objectives, but you've got to convince millions of people to change their practice. Whereas if you want to get CCS out of the ground and off the box, you really only need about 100 companies, mostly from the oil and gas sector, in the room with you to convince you to do it. So those kind of dynamics about what institutions and actors do also play a part in how feasible the rollout of some of these things are. And finally, this point about durable, again, on permanence. The problem with some of these land-based methods, even though they provide all these other co-benefits, they are more vulnerable to losing that carbon in the future through pests, your monoculture issue, fires with wildfires, diseases under future climate change, and just human action, us chopping things down again. So then, in conclusion then, carbon dioxide removal provides a really unique function to being able to limit climate change impacts. When it comes to the scenarios, though, there is a bit of a recurrent issue of some technological optimism around the engineered CDR. It's not been thought through fully. Around policies and scenarios space, there's a seminal paper by Sabine Fuss uses the phrase betting on negative emissions. And there is this real risk of thinking that all this carbon dioxide removal is feasible somewhere down the line, and if it causes us to delay mitigation action, then that does become a problem when it turns out some of that feasibility in those models didn't hold out to be as true. Maybe we don't have as much CDR available, and therefore it's always less risky to crack on with the decarbonisation. And finally, on policy, a shout out to Harry Smith, who's in the room, a second-year critical decade PhD researcher, whose work on betting on forest soils extends on some of the work that Malta actually was talking about with NDCs. He looks at these long-term plans submitted about how countries are going to get to net zero in 2050, and what he's found from his research is that most countries are banking on it being forests and soils doing all the work, which causes, as much as there are other benefits to that, it does raise questions about how feasible the amount of carbon dioxide removal will be and how durable that will be. Just to the final note that this is not all my work, this is very much collective work, so shout out to a range of people across recent projects there at the bottom. Thank you very much.
Right, so we're probably at time now, and we want to have a 5-minute wrap-up from Tim at the end. So is there one pressing question?
No, they're okay.
So anyway, NEM can be got afterwards, I think, anyway.
I've got to teach at 1, so
okay, yeah. Anyway, well, for 5 minutes. Okay, yep. I'll pass over then now to Tim. Would like to come back and just say a few sort of summary words.
Yeah, thank you. I won't keep you for very long. Thank you all for being here. We had this as a morning session because 2 of our speakers, as you know, were in Australia. It's now very late, even for them. Even though we had a morning session, it's now very late for them. So thank you, especially to Jean and Malta, for staying up late. Yeah, I won't show the slides. I think I'll just wrap up and say, yeah, it's been a busy time planning on celebrating our 50 years in the Climatic Research Unit. This is our final research-based event for 2022 around the CRU's 50th. I really enjoyed all the talks today, so thank you to all the speakers. Thank you for the audience online and for the audience in the room for coming. And I think I'll probably stop there. So let's have a round of applause for everybody who contributed. Thank you.